everyone. So far in this chapter, we've been talking about the exponent properties and how those work, and now we're going to start applying those to exponential functions and their graphs. So the first thing you need to know is what is an exponential function. The definition of an exponential function is a function that has a constant as the base and a variable is the exponent. It's helpful to know that they are non-linear, meaning they're not a straight line. They're not going to be able to be put in that form y equals mx plus b, because that is only for linear functions. So this is the first function we're talking about that is non-linear. Here's what the form for this function is going to look like. It's going to be y equals, or f of x equals, a b raised to the x power. So a and b, we'll talk about what those mean in a minute, but x is the exponent and that is the variable. X is the same as what it has always been. It's the independent variable. Something new that's going to happen with exponential functions and their graphs is called an asymptote. An asymptote is an imaginary line that the graph approaches, but it never actually touches it or crosses it. You'll see more of what an asymptote is once we get a graph, and I'll come back to that word to show you an example. So if we're looking at this parent function, f of x equals a b to the x power, or y equals a b raised to the power of x, there's a few points that are special. When we plug in -1, 0, and 1, some special things happen. So let's take a look. If we were to take this equation, y equals a times b to the x power, and we replace the x with a -1, let's see what happens. Based on what we learned earlier this chapter, we know that we're not supposed to have negative exponents. So in order to fix that negative exponent, we know that we're going to take the reciprocal of the base raised to the positive power, the opposite. So now b to the first power is just b. So we have a, we can put that over 1, multiplied by 1 over b. A over 1 times 1 over b, we multiply straight across, we get a over b. So whenever you plug in -1 for x, you're going to get whatever the a value is divided by whatever the b value is. B is the base that the exponent is on. A is if there's any number in front of that, multiplied on the outside. So that number multiplied by on the outside, it's not raised to the exponent. Let's see what happens when we put 0 as our exponent. In earlier this chapter, we learned that a 0 exponent is always equal to 1. So b raised to the 0 power is just equal to 1. So that gives us a times 1, which we all know is just a. So anytime you have the x value of 0, you actually just get whatever a is. Now, if there is not a number in front of the base, multiplied in front of the base, you can assume that the a value is 1. Let's see what happens when we plug in a 1 for our exponent, or our variable. If we put in a 1 for x, we get a times b raised to the first power. B to the first power is just equal to b, so we get a times b. So when x is 1, y is just a times b. So it's kind of helpful to know these 3 points, but you don't have to have them memorized, because if you know your laws of exponents, you can always figure them out. Let's now use those 3 points to get an example of our 2 different types of graphs that we might see. Depending on whether the base is greater than 1 or between 0 and 1, you'll get either exponential growth or exponential decay. So let's take a look at exponential growth first. With a base greater than 1, we might use this example, 4 times 2 raised to the x power. In this case, a is equal to 4, and b is equal to 2. So this time the base is greater than 1, because 2 is greater than 1. Let's see what the graph looks like when the base is greater than 1. We said it is called exponential growth, so hopefully that'll help you understand why our graph looks like this. If we were to plug in -1 for the x value, we know we just said we get a divided by b. In other words, for this function, it's 4 divided by 2. 4 divided by 2 makes 2. So if I put that together, my point should be x is -1, y is 2. Let's do another one. When x is 0, we said that the y value is always equal to a. So in this case, a is just 4. So my point is going to be 0, 4. Next, for the x value of 1, we always get a times b. So in this case, we get 4 times 2, which equals 8. So I know I have a point at 1, 8 on my graph. These are the 3 special points that you'll want to base your graph off of most of the time, but let's say you wanted to get more points on your graph. In that case, you can just plug in whatever number you want for x and figure out what the y value is based on your exponent properties. So let's say you wanted to replace x with a 2. So you would have 4 times 2 squared. Remember, exponents come before multiplying. So you have to do 2 squared first, gets 4. So we have 4 times 4, which equals 16. So that's telling me that I have a point on my graph at x is 2, y is 16. So now let's plot all these points and see what this graph actually looks like. -1, 2 is on the graph. 0, 4 is on the graph. 1, 8 is on the graph. 2, 16 is on the graph. And if we were to plug in another number like 3, we would have the base of 2 cubed. So that's going to get an even bigger number. So we know this is going to keep growing on the right side. It's going to keep going up. Whereas on the left side, let's see what happens. Let's plug in another negative number for x. Let's say we wanted to plug in -2. So that would be 4 times 2, replace the x with a -2. I know that to deal with a negative power, I have to bring the base to the denominator, so that's going to be 4 times 1 over 2 squared. 2 squared is 4, so I get 4 times 1 over 4. 4, you could write as 4 over 1. 4 over 1 times 1 over 4, you can reduce your 4's to 1 and 1. So we just actually end up with 1 times 1, which gives us 1. So we have a point at -2, 1. That's going to be here. No matter what number you plug in, you're never going to get 0 out of the function as the y value. No matter what you plug in for x, you're never going to get 0 for y. You're also never going to get a negative number for y. So what this means is that the graph is going to get closer and closer and closer to the x-axis, but it's never actually going to touch or cross the x-axis. The y values could get smaller and smaller and closer to 0, but they're never actually going to equal 0. That's the graph of exponential growth. It always looks like that, where it's closer to the x-axis on the left end, and it's increasing exponentially on the right end. Now let's take another example for exponential decay. We could use a similar example where we have an a value of 4, but this time our b value is 1/2. Anytime the b value is between 0 and 1, that creates exponential decay. So let's see what that graph looks like. We know when x is -1, the y value is a divided by b. So we have 4 divided by 1/2. In order to divide a fraction, you keep, change, flip, so you get 8. That leads us to the point -1, 8. So let's put that on our graph. -1, 8 has to be on our graph. Next, when we plug in 0, we always get a. Our a value here is 4, so that gives us the point 0, 4 must be on our graph. When you have an x value of 1, we do a times b, so 4 times a half. You could put your 4 over 1 if you need to, and you can reduce that. 2 and 4 can both be divided by the factor of 2. 4 divided by 2 is 2, so we end up with 2 times 1, which is 2. So when x is 1, y is 2. These are our 3 key points, but let's add on some more points like x is 2. When we put in 2 for x, let's see what we get. We have 4 times 1/2 raised to the second power. And we know that in the last few lessons we learned that a fraction raised to a power means that that power has to go on both the numerator and the denominator. 1 squared is just 1, 2 squared is 4. So we end up with 4 times 1 over 4. We can again reduce this. 4 and 4 can both reduce by the factor of 4. So we end up with 1 times 1, which is 1. So when x is 2, y is 1. So that gives us this point here. You might be noticing that our graph really does look similar to the other graph, except it's flipped. So this time, it's called exponential decay, because if you read your graph from left to right, it's going down or decreasing. These graphs do have some things in common. They both have the same domain. You're allowed to plug in any value for x. Notice the graph goes forever to the left, forever to the right. On both graphs, forever to the left, forever to the right. So the domain is all real numbers. Or you could say, if you wanted to put it in interval notation, you could say negative infinity to positive infinity. Or if you wanted to put it as an inequality, you could always put negative infinity is less than x, which is less than infinity. So it's saying x is between any number between negative infinity and positive infinity. Those are 3 different ways to say the same thing for the domain. Now for the range, we're talking about the y values. You might notice that these both have the same range also, because neither one of them crosses this x-axis, but it goes up forever after that. We could highlight everything above there. Same thing here. It never touches or crosses the x-axis, but we could highlight everything above there because it goes up forever. So for both of these functions, the range is y has to be greater than 0. If you wanted to put that as an interval, you would say parentheses 0, comma, infinity. The reason why you're using the parentheses next to the 0 is because you never actually reach y equals 0. It's just greater than, not equal to 0. Next, we're coming back to this word asymptote. Both functions have the same asymptote. Both functions share the asymptote y equals 0, because this line right here, this horizontal line, is the line that the function gets closer and closer to. The graph gets closer and closer to that, but it never touches it or crosses it. So we'll say it has a horizontal asymptote at y equals 0. So remember, that's an equation for a horizontal line is always y equals whatever the y value is, or whatever the y-intercept is. And in this case, it's y equals 0 because it just lines up with the x-axis. Next, they both share the same intercept. They don't have an x-intercept. If there's a horizontal asymptote on the x-axis, that means it never touches the x-axis. So there is no x-intercept. However, the y-intercept is always going to be when x is equal to 0. Earlier on, we said that when x is equal to 0, y is always equal to the a value. Since these two functions had the same a value of 4, they do both have the same y-intercept. The y-intercept is always going to be the same as the a value. So let's write that down. There's no x-intercept, but there is a y-intercept, and it's always going to be at 0, a. That's the point for the y-intercept. 0, a, because when you plug in 0 for x, which is what you always do for y-intercept, you always get a for the y value. All right, now we're going to take a look at another example of graphing. This one says graph y equals 1/3 raised to the power of x. Find the y-intercept, state the domain, range, and equation of the horizontal asymptote. So what I would suggest is make a little table here with -1, 0, and 1. If you're not sure, if you don't want to memorize that a over b, a times b for the y values, you can always just plug in the x value for the x to find y. So for the x value of -1, we're plugging in -1 for x. We know that a fraction raised to a power means that that power has to go on both the numerator and the denominator. We also know that we're not allowed to have a negative exponent, so we have to flip it. If it's already on the bottom, we move it up to the top. If it's already on top, we move it to the bottom. Now we can go ahead and figure out 3 to the first power is 3, 1 to the first power is 1, 3 over 1 is 3. If you put this together as a point, x is -1, y is 3. So I'd put -1, 3 as a point on my graph. If you were trying to do this one with the values of a and b, you're going to figure out b is the base. That's whatever the exponent is on. And you might remember I mentioned this earlier. If there is no number in front of that, that just means that your a value is 1. So if you were trying to do this with a divided by b, you would have been doing 1 divided by 1/3, which would still end up giving you 3 for the y value. Next, we put in a x value of 0 to figure out our y. This is going to give us our y-intercept because whenever x is 0, it's the y-intercept. But we know anything raised to the power of 0 is always 1. So when x is 0, y is 1. Next, when we plug in a 1 for x, we have to put that power on both the numerator and the denominator. 1 to the first is 1, 3 to the first is 3. So we get when x is 1, y is 1/3. So you're just going to estimate, okay, that looks like about 1/3 of the way. And I know that this is exponential decay because the base is between 0 and 1. So I knew my graph was going to be looking like it was decreasing. And all you have to do is go ahead and connect that as a smooth curve. All right, now we're going to do all the parts that they asked for, the y-intercept on this one. It's always 0, a, and we found out that it was 0, 1. The domain for all of these functions is all real numbers, or -infinity to infinity. The range for this one, it is always above the y-axis. So it goes 0, infinity, or y is greater than 0, if you wanted to put it as an inequality. And then last but not least, the equation for the horizontal asymptote. This one is also going to be y equals 0, because that's the horizontal line that the graph gets close to, but it never touches it or crosses it. I'm going to abbreviate HA for horizontal asymptote at y equals 0. As a tip, the horizontal asymptote, this y value, will always match that y value in the range. That could be helpful for some people to see that connection. When you're ready, go ahead and try this practice problem, and you can check it when you're finished. Then you're finished with the lesson for today. And when you come back, we're going to be talking about actually writing these equations based on a graph or a description or given 2 points. So I look forward to seeing you then. Bye, guys.